Benefits and challenges of virtual power plants. In the energy scene, the concept of virtual power plants, or VPPs, has gained significant attention since the accelerated rise of renewables, electric vehicles, and heat pumps. A virtual power plant is a technology and software-driven approach to energy generation, distribution, and management. It optimizes the use of smaller, decentral energy resources, considering the real-time overall situation of the electrical energy system, considering energy prices, costs, demand, supply, grid utilization, weather, and more of a region or country at any given point in time. A VPP allows decentral energy asset owners to create additional income opportunities or avoid energy procurement costs versus the do-nothing alternative. There are also significant challenges for virtual power plants. Given the extensive use of operational technologies as well as public and semi-public communication and data infrastructures, virtual power plants are highly exposed to cyber and data security risks. They therefore increase the threat surface for the energy industry exponentially, for example, denial of service attacks, false data injection, tampering, and more. Therefore, effective cyber and data security strategies are required, and countermeasures must be implemented. Benefits of virtual power plants. Decarbonization and enhanced grid reliability. Virtual power plants promote decarbonization and the use of renewable energy and reduce the reliance on fossil fuels. They distribute energy generation across a network of decentralized resources, making the grid more resilient. This distributed approach can help minimize the impact of power outages and improve overall grid stability. Driven by the electricity, for example, renewable storage, mobility, for example, integration of electric vehicles, and heating transition, for example, integration of heat pumps, grid capacity bottlenecks will become the new normal. Virtual power plants can partly solve this problem via efficient integration of flexible energy assets delivering balancing energy, ancillary services, and more to the grid. Efficiency. Virtual power plants optimize the use of energy resources by aggregating and dispatching them based on real-time demand and market conditions. VPPs ensure that energy is generated and utilized efficiently. They support integration of intermittent renewables, stabilizing the energy system. Demand-side flexibility, cost optimization. Virtual power plants enable demand-side flexibility, allowing participants to adjust their supply or demand in response to price signals and/or grid conditions. This helps to lower energy bills and reduces the need for expensive grid extensions or high-cost peak capacity. In addition, energy asset owners can generate additional income via bilateral OTC, wholesale market, or ancillary services market deals. Security and business challenges. Virtual power plants fully rely on IoT devices, software, and communication technologies, and therefore are heavily exposed to cyber and data security risks and vulnerabilities. Given the decentralized nature of a VPP, traditional security strategies like air gapping cannot be applied. These approaches are also not fully secure in more centralized energy situations like conventional generation, large-scale solar, and wind. Emerging virtual power plants also need to consider financial viability due to various elements of price uncertainty. Technology challenges. Virtual power plants are very complex systems. Different energy assets in the VPP are owned by different entities, and often the service is run by a third party, often called aggregator. Secure data interoperability, governance, and proof of delivery needs to be secured. Diverse energy assets, for example, different types of assets, different hardware vendors, and their integration and the deployment of advanced monitoring and AI control systems is a very complex task. This requires sophisticated software and hardware technologies. Interoperability and compatibility between different energy technologies and devices is challenging, and interoperability standards must be established to facilitate seamless integration. VPPs also need low latency because they must respond to developments in the energy market within a few seconds. Different assets and technologies lack common cyber and data security frameworks. These would help to increase the resilience against malicious attackers. data security and privacy challenges. The reliance on digital infrastructure and communication networks exposes virtual power plants to cyber and data security threats. Protecting the data generated by and commands transmitted to VPPs is essential to prevent unauthorized access, data breaches, and potential disruptions to the energy system. Additionally, concerns about privacy must be addressed, especially when VPPs collect and analyze consumer-related energy consumption data. Business challenges. The upfront investment required to deploy virtual power plants can be substantial. This may be a barrier for smaller players. VPPs must rely on revenue streams, and regulators can incentivize flexibility from virtual power plants, supporting their business case. Electrical energy markets have a limited predictability, and participants will face at least some risk exposure, a lack of open standards, and limiting the ability to switch assets between different virtual power plants, for example, by hardware suppliers creating a lock-in into their virtual power plants, are an area of concern and should be addressed by regulators. Conclusion. Virtual power plants are here to stay and will rapidly grow, becoming a substantial part of the energy system. They are an efficient way to enable demand-side flexibility, which is widely recognized as a key ingredient required to decarbonize the energy system. With virtual power plants on the rise and given their distributed nature, cyber and data security aspects require extra attention. Centralized system security was managed quite effectively, at least in the past. VPPs completely rely on decentralized assets, IoT and software, requiring new security technologies, innovations, and secure system-oriented strategies and actions.